Alright, so we're going to show you how to do an ANOVA. This is going to be just a one-way ANOVA between subjects using JASP. So I'm going to use our assignment 10 data, and we're going to do a one-way ANOVA, and we're going to do a couple here. We're going to do one with gender, and I'm going to show you how the results for the ANOVA are going to be the same as if you were just to do an independent sample t-test. We're going to start there just to show you the overlap here. Then we're going to do one for the variable that we would have to do it because it has 3 levels, and that is for treatment. So we have 3 treatments: psycho, pharma, and control. So we would have to do an ANOVA here because we have more than 2 levels of our independent variable. So let's take a look first at doing it for gender, and let's see how the t-test and the f-test for the ANOVA compare. So if we do an independent sample t-test, and we're going to look at the effect of gender as a grouping variable on pre-levels of manic symptoms, we get a p-value of 0.863 and a t-value of negative 0.173. All right, so this is what it looks like if we do an independent sample t-test. Now what if we do an ANOVA for the same effect? So now we're going to look at gender as our fixed factor, and we're going to look at how that affects the same variable pre-level. Look at these p-values, 0.863. Look at the DF terms. They're the same, right? Notice the independent sample t-test never gives you a numerator, right, degree of freedom. It only has one DF term because there's only ever 2 groups. So because this number would always have to be 1 for this test, they don't have to report it. It's not a variable. It doesn't change. But the residual, notice, is the same. The p-values are the same. The only thing that's different is the t and the f value. But it turns out that t squared equals f, right? So if we were to pull out a calculator and do that quickly, what we'll find is that negative 0.173, and if we square that value, we get 0.03, right? So the independent sample t-test and the one-way between subjects ANOVA, where there's only 2 levels, male-female, of a variable, gender, it's the same exact test, right? And this is just kind of a demonstration of that fact. So now if we get rid of these results, and let's do a case where we would have to do an ANOVA. We would have to do an ANOVA when we have more than 2 levels of our independent variable, such as we do for treatment. So what does that look like? If we run an ANOVA, the first thing we need to identify is what is the dependent variable. That is, what is it that we think differs between the groups. In this case, we're going to look at the pre-levels of manic symptoms. Okay, so this is how much manic symptoms were measured in the people before they started treatment. And then we're going to look at how treatment, as the grouping factor, fixed factor, how that affects this dependent variable, the pre-levels of manic symptoms. So here's what we find. Treatment, the f value, the p value. Okay, so this p-value is greater than 0.05, so this is not statistically significant. So there's no effect of treatment on pre-level. So if this were a test we were actually performing, that would kind of be the end. We would say a one-way between subjects analysis of variance was performed to evaluate the effect of treatment on pre-level manic symptoms. The f-test was not statistically significant. F of 2,42 equals 0.147, p equals 0.863, period. These results indicate that there were no differences in manic symptoms before treatment between the treatment groups. And that's actually a good thing. What that means is that everyone kind of starts out the same, and you would hope that's the case if you randomly assign them to groups. You would hope they don't differ at baseline. It can happen, but you don't want it to be the case, right? So this is the effect. Now, if you found something that was significant, so if we look at treatment differences at follow-up, not quite significant. So let's look at treatment levels at post. And this is statistically significant, right? P is less than 0.05, right? So here, this significant effect, we need to follow it up. And like we talked about, how do we know if we need a post hoc? 2 things. 1, is the effect statistically significant? Yes. 2, are there more than 2 levels of the independent variable? For treatment, we know that's the case. You can also always tell simply by looking at the DF term. If the DF is more than 1, then there's more than 2 levels, right? Because this is always the number of levels minus 1. So this test has 2 degrees of freedom, which means that we need to do a post hoc for it. Anytime an effect has a DF greater than 1 and a significant result, you need to use a post hoc to interpret it. So we can do assumption checks in here. You can do things like test for homogeneity, right, if you want to. So here, this would suggest we violate homogeneity of variance. We could look at the descriptives and see, how different are those variances? Do we need to be concerned? There are corrections such as the Brown, Forsyth, and Welch test that you can perform to see whether or not the results remain. And what we see here is even when we use these other approaches, the F tests are still significant. So given that, I'm really not too concerned about this violation because it's not substantively changing my conclusions. But as we talked about, there are assumptions in ANOVAs and t-tests and all statistical approaches. So that's worth considering. You also you can look at the QQ plots for the normality of residuals, and this is a pretty good looking QQ plot. So I wouldn't be too worried about any of that. So what we do need to worry about here is looking at the post hoc tests. And so we need to get a post hoc test for treatment. So we open post hoc, slide over treatment, and here we get the Tukey adjusted p-values. And what do we find? There's no significant difference psychotherapy versus pharmacotherapy. So those two treatments averaged across just for everybody, right? Those two things didn't differ. So the treatments weren't different from one another. We find that psychotherapy was significantly better than control, right? Psychotherapy control. And again, the mean difference, it is this number minus this number. So this minus this, right? This number has to be bigger for that to be a negative, like 10 minus 20 makes negative 10. And smaller numbers here are better because it means lower or fewer manic symptoms. So we know psychotherapy is doing better than control, and we know that difference is significant based on the Tukey p-value here. Pharmacotherapy versus control is not quite significant. Okay, so the difference here is driven by the fact that psychotherapy is a more effective treatment than doing nothing. But that's the only thing we can conclude is statistically significant. Now, to fully interpret this, we need to have the means. And you can get the means by going to additional options and getting marginal means. And I suggest you also get descriptive statistics for that as a minimum. And this will help us be able to interpret it. So here what we see, psychotherapy and control was a 10-point difference, right? Negative 10. And that's these two numbers, 9.8 and 19.8. They differ by 10. Right? So psychotherapy 9.8 minus 19.8 equals negative 10. That's where this comes from. Okay? So what we see here is in psychotherapy, people demonstrated significantly fewer manic symptoms immediately after treatment if they were in psychotherapy than if they were in the control condition. And we would report the means and the standard deviations for those things. And we see this is a balanced design because there are the same number of people in each group. Okay? So we would say something like, in order to determine whether treatment had a significant effect on manic symptoms immediately following treatment, a one-way between subjects analysis of variance was performed. This test showed that there was a significant effect of treatment. We would say F, and in parentheses 2, 42 equals 8.728, P less than 0.001, right? And then we would say that these results show that there is a significant effect of treatment, which were followed up by Tukey post hoc tests. The Tukey post hoc test revealed that although psychotherapy and pharmacotherapy, and I would report after those two words, after psychotherapy, I would put the mean and the standard deviation in parentheses, and pharmacotherapy, and I would put the mean and the standard deviation in parentheses, did not differ significantly, P equals 0.171. And although pharmacotherapy and control, and I would put the mean and standard deviation because we haven't reported it yet, did not differ significantly, individuals in psychotherapy did significantly better than individuals in control in that they exhibited fewer manic symptoms, P less than 0.001. So that would be everything we need to interpret these results. You have to have the marginal means. You have to report them to fully interpret because you're testing the difference between means. If you have more than 2 levels of a variable and a significant effect, you also have to have a post hoc comparison to know which ones differ. You can't just eyeball them. You can't just say, oh, 9.8 looks different than 14.2. Can't do that. We have to follow them up. Now, the other thing we can do to interpret this a bit further is we can get our estimate of effect size. So you can get eta squared, partial eta squared. In one-way designs, those two numbers are going to be the same number. So notice partial eta squared and eta squared are identical in a one-way design. Omega squared is an adjusted value that should be lower, right? It's always going to be lower than your eta squared. They are all in the R squared family. They are all essentially proportion of variance explained, right? It's okay to report any of them. I think eta squares are more common, but eta squares might be a little, they might be a little high. They might be a little inflated relative to the effect that would actually exist in the population. So omega squared includes an adjustment to try to make the value maybe more representative of what would exist in the population. I'm okay with reporting either, but in our class, we principally focus on talking about partial eta squared or eta squared. And eta squared, partial eta squared are the same thing as R squared. You could write them as R squared. People just use that phrase eta squared common within the realm of ANOVA. So just fine. And that eta squared is just going to be the sum of squares of the effect over the sum of squares total, not residual, total. Okay. So if you took sum of squares treatment and divided by sum of squares treatment, sum of squares residual, that's going to get you that value. And we'll show you that real fast. So if I take 753.6 plus 1813.2, so 2566.8, 2566.8, I get 0.294, which is eta squared, right? 0.294. So eta squared is just the treatment effect, sum of squares treatment, over sum of squares total, okay? So we just demonstrated that how that's calculated, but you can also just get that under the additional options, under estimates of effect size. There you go. And so this is really a very full interpretation. If you're going to include the effect size in the write-up, which you should, according to APA style, for significant results include an effect size, you would report it right after the p-value. So you'd give the F results, F of 2, 42 equals 8.728, P is less than 0.001, eta squared equals 0.294. So that is a full interpretation here of ANOVA and how you could perform these tests using JASP.